Hello everyone, welcome back to Chemical Engineering and Aspen channel. In our today's video, we will cover a topic which hasn't covered yet, and that is to compare the manual calculations with Aspen simulation. Obviously, the purpose of this channel was to give you awareness regarding the Aspen, all software related to Aspen, which was Aspen HYSYS, Aspen Plus, Aspen Exchanger Design and Rating, Aspen Energy Analyzer. But now our focus, after learning so much aspects related to Aspen, is that we would like to compare the manual results with the Aspen results to check the reliability of our simulations. So for this activity, or for to verify the calculations, we will use the shortcut distillation column, and we will first see the manual calculations, or you can say that our today's video is divided into three parts. Number one is the manual calculations, and to get the results from manual calculations. Number two is the Aspen simulation, and number three is the comparison of both these results. So before starting the video, if you have not subscribed to the channel yet, please subscribe to the channel. Click on the bell icon to get all updates related to this channel. So before going to the simulation, we will first look at the problem description, that a 10 kmol per hour feed flow rate of saturated liquid that consists of 40 mole percent benzene and 60 mole percent toluene. And we have to send this to the distillation column for separation. At the top, or from the distillate, we want 99.2 mole percent benzene, while from the bottom, we want 98.6 mole percent toluene. So it means that 0.8% of toluene is present in the top product, or we can say 0.008 in terms of mole fraction, while 1.4% of benzene is present in the bottom product, or we can say 0.014 mole fraction. The relative volatility is 2.354. The reflux is returned as the saturated liquid, and the column has total condenser and partial reboiler. In our today's activity, we will simulate the process and we will do the manual calculations as well. So the first part is the manual calculations or hand calculations, and in shortcut system we have studied a famous equation which is Fenske Underwood Gilliland. So Fenske is used to compute the minimum number of stages, the formula of which is natural log of x of L key. Now in this system, the light key, L key, is benzene. So the fraction of the mole fraction of benzene in distillate divided by mole fraction of heavy key, which is toluene, in distillate. So we can say that the value of light key in the top product is 0.992, while that of the heavy key is 0.008 in distillate, into x of HK, which is the mole fraction of heavy key, which is mole fraction of toluene in bottom, divided by mole fraction of benzene in bottom. So 0.986 divided by 0.014 divided by natural log of relative volatility, which is 2.354. Accordingly, the answer will be 10.6. So 10.6 or 11 stages are required minimum to operate this process. There is another formula that almost gives the same answer. Then we need to find out the optimum feed stage, which is natural log of x of L key. This is the same correlation which is used in the minimum number of stages, x of L key divided by x of HK in distillate. So 0.992 divided by 0.008 in distillate. However, divided by x of Lk divided by x of Hk, which is x of light key in feed, which is 0.4, and heavy key in feed, which is 0.6. 0.4 is for benzene, 0.6 is for toluene, divided by, again, relative volatility. The answer is 6. So at 6th stage, at least a minimum feed stage should be 6. Second part is the Underwood equation that is used to find the minimum reflux ratio. So the formula is 1 minus q summation I is equal to 1 to n alpha I xi divided by alpha I minus phi. Now the value of q is 1 because it is saturated liquid. For subcooled liquid, the value of q is greater than 1. Then for saturated, it is 1. Then for two-phase, it is between 0 to 1. Then is equal to 0 for saturated vapor, and accordingly for less than 0 for superheated system. So rearranging it, 0 is equal to, now I means the component. So for benzene, it will be alpha B x B of F, which is the mole fraction of benzene in the feed. So alpha B is 2.34. This one is 0.4. Again, alpha B is 2.34. Similarly, for toluene, 1 is the relative volatility, or is the volatility value for toluene. X of T, which is the toluene in feed, which is 0.6, divided by 1 minus 5. And rearranging this equation, the value of phi is 1.528. Then we will compute the value of R minimum. R minimum plus 1 is equal to summation alpha I xi in D divided by alpha I minus phi. So again, the value in distillate for benzene and toluene, alpha B, the value will be 2.354. X of B in distillate is 0.992. Phi value is 1.528. Similarly, alpha T 1, X of T 0.008 divided by 1 minus 1.528. So the R minimum plus 1 value is 2.82, and the value of R minimum is 1.82. So this is the minimum value of reflux ratio. But if you want to calculate the actual value of reflux ratio, the range is 1.1 to 1.5 times R minimum. It means that we have to multiply the minimum reflux ratio with a range of 1.1 to 1.5. So selecting 1.1, accordingly the answer will be 2. Next part is to calculate the actual number of trays for the given reflux ratio. So we use the Gilliland method, and that is n minus n minimum divided by n plus 1 is equal to 0.75, 1 minus r minimum divided by r plus 1 whole raised to power 0.5668. So n minimum is 10.59 or 10.6, r is 2, r minimum is 1.82, r is again 2. So solving this equation, we get the number of stages as 28. 28 number of stages are required for this system. Then optimum feed tray, n of D divided by n of B is equal to x of F in heavy key, light key, heavy key B and D, and flow rate of bottom and distillate. Now we don't know the flow rate of bottom product and top product, so applying the mole balance, we get this equation. Substituting the value of Z for benzene balance is 0.4. X of B in bottom is 0.014 of benzene mole fraction. X of D 0.992, X of B 0.014. Flow rate of the feed is 10, so accordingly the distillate flow rate is 3.95, and the bottom flow rate will obviously be 10 minus 3.95, so it will be 6.05. Now this is one correlation, but we will use this correlation, which is the Kirk-Bride method. Natural log of ND over NB is equal to 0.206. Natural log of X of heavy key divided by X of light key in feed. X of light key divided by X of heavy key, light key in bottom, heavy key in distillates, square root B over D. So substituting the value of X of H key 0.6, L key 0.4, light key in bottom, which is benzene, so it is 0.014, heavy key in distillate, which is toluene, 0.008, 6.05 divided by 3.95. So accordingly, when solving it, we get the value of NB as 11 and ND as 17. So there are 17 number of stages from the top. That means that the feed tray is the number 17 from the top. So there are 28 stages in the system. 17th is the feed stage. So we will now go to the Aspen HYSYS and we will simulate it, and in the third part we will compare the results. So coming to the simulation, we will first add the components benzene, toluene, and we will select the property package as Peng-Robinson. Then we will go to the simulation. In separator, we will select the shortcut distillation column. We will do the connections, feed, condenser, duty, distillate, the boiler duty, and bottoms. The top product is liquid as has been confirmed to us. In worksheet, we will specify vapor fraction as 0, and the pressure is 1 atm. The flow rate is 10 kmol per hour. Benzene mole fraction is 0.4, toluene mole fraction is 0.6. Then we will specify the key components. Light key in bottom, which is benzene, which is 0.014. Heavy key in distillate, which is toluene, that is 0.008. The condenser and reboiler pressure are 1 atm each. And we get the minimum reflux ratio as 1.824. Multiplying it with 1.1, we get the answer of 2. So this is how we simulate the shortcut distillation column. A bit speedy, but obviously we have covered it in our previous videos as well. So we get the minimum number of trays as 10.66, the actual number of trays 27.998, optimal feed stage 16.777. So this was our second part of the video. Now moving to the third part, we will compare the results. If you remember, the minimum number of trays were 10.6, while here it is 10.66. So both results are comparable. Then actual number of trays 28, manually 28 with Aspen. The optimal feed stage was 17. Just a few moments ago we have said it, and optimal feed stage is 17 over here. The minimum reflux ratio was 1.824. In manual calculation, it was 1.824. The actual reflux ratio was 2 over there. Here it is also 2. So you can see all the results are closely aligned or almost matching with the both Aspen calculations and manual calculations. It means that our simulation is reliable, our calculations are okay, and both are comparing with each other. This was the main part or main objective of our today's activity, that we want like to see that Aspen verifies our manual calculations, or our manual calculations are in line with the Aspen calculations. So I hope you have understood all the aspects of this lecture. If you have any queries, feedback, suggestion, please provide it in the comment box and I would be happy to answer it. So that's it from today's lecture. Thank you so much. Please do watch, like, share the video and subscribe to the channel. Also click on the bell icon to get all updates related to this channel. Till then, it's goodbye. Stay tuned for more exciting videos on this channel.